482 if I'm still alive. If I can survive any more accidents. The bravest people are people who aren't CS and they take Math 482 as an elective. And then they get surrounded by all these programmer guys who know all the terms, and it's like they feel like, wow, these guys have all this background and I don't. They feel kind of naked there, But it's funny when it comes to I do the same thing with the groups, work in groups. When they make a group, you know what those computer guys want? They want a math person in there. Because the die now and then puts in a proofy kind of problem. They need that. It's insurance against math style problems. All right. Let's see. So I'm trying to get out of chapter 4. I've been trying to do that for 4 months, but I'm doing my best. Yeah, I see that. You do this. Hey, what's that? I'm sorry. I'm slow. I'm like a turtle, but I'm just the way I operate. I'm not. I don't write really fast. I certainly think really slowly, like a turtle. Okay, so let's. What were we talking about? We were talking about the Poisson, right? So x equals Poisson with parameter lambda. And what was the mass function for that? So probably that x equals I. What was that? What was the mass function? Just like a whole fleet of helicopters just went over. What was that? It was e to the minus lambda times what?
Lambda to the I over, was it I factorial? I think so.
Lambda to the I?
I think so.
So this models some interesting things. So I thought we would just do one really quickly. Yeah, it sounds like a military helicopter or something. Anyhow, so the probability of being dealt a full house. Or a full house in 1,000 hands is what is it? It's about 1.4. So the question is that they were asking here. This is 4.61. What they're asking is, what's the probability of being dealt at least 2 full houses in 1,000 hands? So you want to get the probability of x is greater than or equal to 2 in that situation. So what is our usual way of doing a problem like this? I don't want to sum up an infinite series, right? Especially not today. So what is the what's the recommended way to do this? Well, you've got a lot of cases. X could be dealt 3 full houses, 4, 5, 6, 7, 8, 9, 10, 11, like that. But it's better, to look at the complement, right? So what would the complement be? The probability of no full houses minus the probability of exactly 1 full house. All right? Okay, so the only thing that I haven't done is I haven't connected this to lambda. So what would be the n here? N is, if you're using an approximation, a Poisson approximation to the binomial, which is what's happening here, n is assumed to be usually large and p is small. But we're exactly in that situation. It's some small probability.
Just to clarify what this is, the probability of a full house in 1,000 hands, is this saying that we expect to see 1 point, like the expected value
Yeah.
is 1.4? Okay.
Right, exactly. Then you said, yeah, I should have said that, and that's what I was going to do here. That this is the NP here is 1.4. So this is moderate, right? And the P is small and it's large. This is ripe for the approximation with the Poisson. Okay, they set it up that way. So it's been set up. So when they, well, how could it have been set up differently? Well, they could have said, what's the probability in a given hand of getting a full house, right? And you could have done it precisely with the binomial distribution, right? So anyhow, what is this? It's going to be 1 minus 1. Let's look at this mass function over here. When x is 0, these two terms, 0 factorial is 1. So this lambda to the 0 is 1. So it's just e to the minus lambda. What's lambda? Okay? And that's when x equals 0. When x equals 1, you still get e to the minus 1.4, but then you have this lambda to the 1, which is 1.4. And that's the approximation here. Let's see what it is. I didn't do it. But anyhow, Ross says 0.4082. This is Ross. I got it from the back of the book. So I'm doing a little cheating, but that's what it should be. We should probably check it on a calculator. So the probability of getting 2 or more is almost, it's getting up there to 50%. So you see, it's stated a little. We could do this precisely. I wonder how far away it would be from the if we use the binomial. But I'd probably have to use some software or something to do this. I probably think. Well, I don't know. Well, I'll leave that as an exercise for you guys to do. If you did the binomial, well, what would it be? I mean, I have to know I don't know the probability of getting a full house on a given hand, and we could look it up. It's in Ross, right? It was a problem. We did it in class. So what was that? I'm curious now. This is the bad thing about being curious. Okay, so what is the probability of a full house? I don't want to go over it because it was sort of complicated, but do you remember from the book? It was the problem that was done earlier. Let me look for it. I don't know. When I'm looking for something, I'm not likely to get it. Oh, wait a second. Okay, I found it. 0.0014. So it's okay. That makes sense. 0014. So if you're going to set this up, okay. And so you're going to do this now. I'm going to put x as binomial. So x is binomial what? 1,000, right?
1,000 trials and probability of success 0.0014.
Good. So I'm just curious. I'm going to leave this here. So I get the feeling this approximation is going to be very good, but I can't do it unless I actually do it. So this is 1 minus, what's the binomial? Well, if you don't get any, so what's the chance that you don't get any? Well, this 1,000 choose, it's just 1 times what? That you don't. Sorry, I didn't prepare this, but I'm just determined to do it now. So the probability that you don't get any success. So this is the success probability. So not getting one, well, you have to do 1,000 reps, right? So it's, what is it, 0.9986 to the 1,000? And what about this? So this is the, and you gotta have a calculator for this. What about this? What's the chance of getting one? Well, n is 1,000, right? So there'll be 1,000 times you get one success. 0.0014 and times what? 0.99. And hopefully I'm not doing anything stupid, which is I've done before. So this number, I don't know, I need a calculator here. And of course I'm hoping that that's going to come close to this. It's not impossible to do this, but it was easier to do with a Poisson approximation. So what is this? What is this?
I do have a calculator, and let's see here. It's not. I mean, it's kind of close, but not very.
Be a number, or you don't-
0.59.
Okay, say that again.
0.59.
Okay. Well,
if you're okay with being, zooming out a whole lot, it's close.
I'm just surprised that it's not better than this.
Yeah.
Because this is, if you did this, so you got 1,000 times 0.0014.
I'm gonna check my work one more time, but
I'm sure you're right. It just shows you when
yeah.
when you have an approximation, it may not. I wonder why it is not better than that. Anybody else do it? We're gonna chat. Maybe somebody else did it on the calculator and see if that's what they said. Yep, you're right. What is G? Where's the G? I didn't write a G. I didn't mean to. Where is the?
Oh, Professor. Okay, well, first off, it's where you wrote the binomial. Your comma looks like a G.
Oh, yeah. Okay, I was trying to emphasize that it's a comma.
Yeah. I did make a mistake on my in my calculator. It is much closer. 0.408.
0.408.
08.
That's pretty close, and so it ends.
Yeah, like the next number is 3, but it's
good. Well, that makes me. That makes
I was like,
because
yeah, you're right.
Because it's it's not exactly the same. If it's exactly the same, I'd be really suspicious. I get start getting suspicious.
Oh, you know what? I forgot the 1 minus. It was literally the 0.59.
Oh, yes.
Yeah.
Right. That's what happened. Okay, so since we're doing this binomial nut crazy thing here, or I'm the nut. I once got, I got my PhD at USC, and I still get on their mailing lists, and they send me the glossy now and then, and they always ask for money over the phone, and then I don't give it because I don't feel rich enough to do it. But they have a school of geriatrics. Oh, why is somebody asked the question, Brandon asked, why is 0.99? Oh, wait, which one? This one right here? Because this is the probability that you don't get, this is the fail probability, right? So the probability that you don't get any successes, well, that would be just, but these are independent trials, right? We're assuming, they're not, they're independent trials. And this you'd have to get fails, and you have to get 1,000 fails. In other words, you didn't get any full houses in 1,000 hands. So this is a probability of failure. And does that make any sense, Brandon?
So the exponent determines how many iterations?
Oh, that if in the binomial you still have 1,000 iterations, right? But in this case, you had 1,000 that were fails. Somebody asked something else. This is from checking how accurate plus I use it. Yes.
So you check it 1,000 times then?
How to say this? You think about it this way: that somebody's dealing. You have a deck, right? Full deck, and then you deal it out five hands, and then you see whether you got a full house or not. And then the next time you do, you shuffle the deck and you do it again. So there's no dependence between the successive hands here.
Mhm.
So you can think of it as 1,000 trials. Okay, you've been dealt 5 cards 1,000 times, 1,000 trials, right?
What happened to the 0.59 answer? Because now it's 0.40.
Oh, I think that when she did 0.59, I have the feeling that it might have been for this. We needed to subtract
Yeah,
off.
that was my error. I just did the x equals 0 and
I
x equals 1 and sum them. But yeah, I forgot to do 1 minus minus. And I
Yeah.
got the right answer that way.
Yeah.
Or it was very close to the Poisson approximation.
Okay, guys, it's time for the story now. The story is it's bedtime story now. Anyhow, so the School of Geriatrics, they sent me a glossy, and in there they said if we didn't age, how long would we live? Okay, if you didn't die from anything related to age or disease, how long would you live? And when I present this to most lower division classes, they say you would live forever. Well, I happen to know, I have personal knowledge of this. Now, I was in an accident yesterday. I was like, luckily nobody was hurt, but I easily could have not been here permanently. But this is an interesting question. And so the glossy, they made a calculation. So they, well, first of all, how long do you think you'd hang in there on average? With the probability is 50% that you would live at least so many years. If you didn't have any aging going on and no diseases going on, how long would be the average? 50% would live to be how old? Just give me a number. Give me a number.
Brandon's guessing 110. I'd probably something like that, like 100.
We can calculate it, you guys. We can actually calculate it once we have the calculator at our disposal. So you can think of each year as being a trial, right? So it turns out that the most long-lived, let's see, when you have adolescent kids, maybe 16 or 17, or maybe a little younger, they last the long. Their chance of dying or living to the next year is something like this. Probability of living, so your success probably getting to the next year is 0.995. So, gosh, I should have prepared this better. But these years are independent, so you have to calculate at what point do you get to the 50% marker. So every year have this chance of going on. So when does this get down to 50%? Okay. So it's an interesting fact. You can do this on a calculator, I think. You have to solve for it. You can take logs or something like that, but I really feel I should do it on my calculator. How should we solve this?
Can you explain the question one more time? I don't think I.
Okay, if they, this is the School of Geriatrics, so they're thinking they're thinking big. They're saying, well, we're going to get rid of aging. People ain't going to get older, and they're not going to die of diseases. Especially age-related disease. They don't want to die of anything like that. What does that leave? I mean, the GE people say, well, they'll live forever. Well, what does it leave? We're missing something. What is it? What could you die of? Accident, right? Get mowed down by a car or something, or an auto accident or something like that. So if this is the probability of going on to the next year, if you're like 15 years old or something like that, when it's very little chance of it's just this is like aging and disease are not a part of this picture. It's just accidents. So the question is, what does this end when this cranks down to? Because one of the probability of lasting in years, right? And they're independent. As long as you haven't died, they're independent. So you just treat each year as a separate trial, right? How many trials do you go before your probability of keep on going? Is 50%. That's the calculation. Does anybody have a calculator who can do this? I think you.
I've already done it.
Okay. Let me guess. When I recall did this before, I got around 1,200 years. What did you get?
1385.
That's pretty old, you guys. I mean, it's sort of impressive, you know. So not that the Earth could support everybody, vampire lifespan, but I mean, this brings up, what would social network, how would these dating apps operate then? So somebody would say, I'm 800, I'm only 800. I don't know. That doesn't sound very good. It would give new meaning to the word ancient, But of course, USC isn't concerned with that. They just want more contributions till they can find the keys to stopping aging. But this is an application, I guess, of the binomial thing. This is a sequence of repeated successes, What's the probability? Because they're independent. So what's the probability? Well, it's the product of them. So you have the product of n trials. And so the probability of going that far is 50% when you have 1385. Okay, I hope that found that interesting. It's the true fact. It's amazingly high. Vampire lifespan, 110. You're going to live longer than 110, man. All right. So we'll go from that to ESP. Let's do a problem on ESP. Okay, so 4.41, I'm just cleaning up the best problems that are in the book. So 4.41, man claims to have ESP. So how do we write that sentence? Does he have ESP or not? And you toss a fair coin 10 times. And before he knows the outcome, he's going to guess, or it happened, he didn't see it happen, but he's going to say, well, these were the outcomes. So this man got, he got seven right. So this person gets seven correct. What I mean by getting seven correct? Well, he didn't see the toss, but he's thinking and he's saying, okay, it's heads or tails, it's fair coin. So, but he managed to hit it, hit seven of them. So the question is that evidence that he has ESP? So how do you phrase this mathematically in terms of binomial probabilities? So what do you have to do? I mean, if the question is how likely would this be to happen if he's just guessing? Well, first of all, before we do it, let's just set this up. I mean, do you think if you get seven right, that sounds pretty impressive, right? And if you really do this properly, you should really say, well, it's more than just getting seven right. It's maybe you got 8, 9, or all of them right? I mean, it's kind of like that's the range where you really should be looking. But what is the probability that if he's just guessing, he gets exactly 7 correct? Let's put it that way. So this is binomial what? So this is binomial 10 reps, and that's probably a half. And we want to calculate the probability that X, let's just say, 7, even though, I think there's something wrong with the problem in the book. They should have 8, 9, or 10, but let's just calculate this. How do we do it? Well, to get exactly 10, you tell me. 10, choose 7, and you got 7 of them. So what? I mean, both the ones you got right and the ones you didn't, they all have probably a half. So it's a half to the 1. And I don't know what 10 choose 7 is. I did this on a calculator at home, but anyhow, I know that 2 to the 10 is 1024. What is 10 choose 7?
120.
Thank you. 120.
120. So this is about equal to what? 1172. So how do we interpret this? I mean, this is what I would do. I felt like the problem was incorrect because he didn't have 8, 9, 10. It's highly unlikely he's going to get all 10 right, 9. I mean, this is really, if we get, this is probably the math, the most, the meat of it. So if he's just guessing and he gets 7 right, it's a fair coin. For that to happen, the likelihood of that by chance is really low here. And the way statistics works, if you're like under 20%, you something's up. So this is how you compare. This is how you answer these questions. If somebody's done something like this, then you might argue, well, wait a second, let's do the experiment again and again and again. But that's not how statistics works. You set up the experiment, it runs once. Okay, and this is the real problem. If you've looked up ESP on Wikipedia, there have been some experiments that ran once, but they were overwhelmingly positive for there being ESP. But then it was very difficult to repeat them. Let me just check this in the book. I'm sorry, I'm just kind of moving very slowly today, but let me just check in the book that they didn't have the rest of it, of the binomial. Yeah, it's one of those days I'm moving slowly like a turtle. Well, you know what? I didn't read this thing carefully. I didn't read this very carefully because there wasn't at least 7. So 7 is one of the outcomes. The book did say at least. My apologies. So we would have needed to add 8, 9, and 10. But I think, like for instance, I think 10 is really.
Well, since it's it's 1/2, then it's not too bad. So 10 choose 8 is 45. 10 choose 9 is 10. So you can just add 120 plus 45 plus 10 plus 1.
Let's see how that changes it. Let's see how it changes. Because I know that if you have 10, it's essentially 1 over 1024. So it's like 0.1%. It's not going to happen. So, okay, could you say, Aim, what you have there? So
45, that's 10 choose 8.
Yes.
That's 10, that's 10 choose 9.
10
plus 10.
And there's
And then plus 1.
Right. So what do we get in this case?
0.172.
That's a little different, right? Than when I wrote. I had like 0.11 or something, but we're still in that place where it's below. If it's below 20%, that's in practical statistics. So that's considered significant. Okay. Whether it's an artifact of the experiment or something like that, or but it's significant. So there's something there. Thank you, Aim, for pointing that out. So I knew that I had something fishy there, but. All right.
I thought the P had to be less than 0.01.
Say again?
For it to be, I thought it had to be like 1%. I think I might be thinking.
No. That's a good question. No. This I've taught statistics before. No, in fact, okay. Let's guys help me try to remember. If it's in a civil trial as opposed to a criminal trial, the p-value. This is the probability of something happening by chance. I think if it's a civil trial, you just need a preponderance of evidence. If it's a criminal trial, you need beyond a reasonable doubt, which is much tighter. And I think I remember preponderance is p-value is 35%, but a criminal trial is 20%. So if it depended on this probability being under 20%, you would be there, right?
You said it was, what were the two? It was criminal trial and what was the other one?
Civil.
Civil?
Yes. So
I've never heard of those, to be honest.
Civil trial? Well, the thing is, you something happened, and the question is, was there premeditation? Did somebody do that, or could it have happened by chance? Could this result just have occurred by chance? So you have to decide what is going to be your cutoff, right? And it turns out it's not like 1%; it's something like that. In science, even in science, when you get a p-value of 20%, you can publish that. It's publishable. But there's the assumption there's a real effect. It's not just a random variation in the data collection. But I'm trying to think, what would be a civil case? Well, there's a famous one in Ross. If you're willing to spend the time to read it, this example goes on and on. But it was about the question was whether people were cheating in a game of bridge, in a bridge international championship match, and like whatever happened, they try to figure out, well, how likely would this be to have happened by chance if they weren't cheating? And it turned out that they probably were cheating. But there's a long story. It's like 2 pages, and it's an example in Ross. You might say, who cares about it, or a bridge thing? But I guess there's a lot of story.
I would think that for criminal, it should be way tighter than 20%. I thought,
No.
5% at least.
No.
Less ridiculous.
Think about it. If it's 20%, it's only going to happen once every 5 times, right? I mean, we're talking about somebody's life here or something like that,
Exactly. So, pretty much, there's almost like a 20% chance that you get, off someone who didn't do it.
Well, yeah, but it's beyond you have to have evidence beyond a reasonable doubt. But you're right. You might get somebody who didn't do it, but you might get somebody who's innocent. That's always the problem. But that 20% is what I understand is to be the standard.
That's so weird.
Let me see if there's any more interesting things that I was able to find. Okay, we'll just do one more, okay? And I know this is dumb, but I like doing it. Let me just repeat the thing about a multiple choice test. We did it already, but let's just whip through it one more time. Okay, so again, we've done this before, but I'm just emphasizing it because I'll be on the next test. So multiple choice exam, there's 5 questions. Okay. And what is the probability that you get at least 4 right just by guessing? I know we did it, but I'm going to put something like this in the test. So we're in a multiple choice situation. What is this binomial what? Well, there's 5 questions, and what is the chance you're going to get it? You're going to get it right. What's your success probability here? Well, okay, I didn't say how many answers are possible. 5 questions, and each has 3 possible answers. So you have to fill in the blank. There's answer A, B, and C. So what's the success probability here? 1/3, right? So to answer the question, you want at least 4, right? So what's the probability that you get 4 and the probability you get all 5 right? Just by guessing. What's this going to be? I know this is easy. I feel bad to do something so easy, but I like it. So if you get 4 right exactly is what? What's the binomial mass function for you? Okay, 5 choose 4. You got 4 right. And then you got 4 right and then 1 wrong. The chance of getting wrong is 2/3. What about this? This is you got how many right? All of them right. So if you multiply this out, I got 11 over 243. Whatever that is the decimal. All right. Okay, so let's get back to real things. So I'll cook up something like this. The thing I would cook up is like, you have like somebody tossing a coin, and believe it or not, people in the past did that to, I'm sorry. Can you see it now? Okay, I don't know what the decimal is. But people used to, some people, they would toss a coin repeatedly and keep track of the data. They were curious whether the coin was fair or not. So this is a common thing where you say have 5,000 tosses, and you end up with 2650 heads. So you ask yourself, is this coin fair or not? And what are you really asking when you do that? You're saying what? What would you expect? If it's a fair coin, you're sort of expecting, right, 2,500 heads. So what is this? Where is 2650? But however, you could have more heads than that. So, and whatever going the other way, so how much, we're 150 over, 150 less, 2350. So the way this is handled, and this is sort of the convention, what you want to do is compute the probability that your 2,650 heads or more extreme, okay? So you don't just do it for 2,650, but you want to say, well, what's the chance that I got 2,650 or more all the way up to 5,000? And that's your so-called p-value. If it's really low, then that means that just by chance it'd be very unlikely to get that many or more extreme. Why do we always have to say more extreme? Why do we have to say that? Because the distribution
that gives us the range, right? That we're talking about.
Yeah, but this is a discrete, finite, kind of distribution here, right? It's binomial. But usually these things are modeled by the normal curve, okay? It's a normal approximation to binomial. In this case, your number 2650 comes up here, say, or farther over. And what's the probability of getting exactly 2650? This is I'm foreshadowing the next chapter. If that's a normal curve, what's the chance of, and this is the distribution of the random variable, what's the chance of getting exactly 2650? It's 0, okay? Okay, this is continuous, so this random variable, this normal random variable takes on all values all the way through here. So in this case, you don't have any options. You've got to be calculating this area here. Okay, so let's
basically models this discrete problem as a calculus problem, doesn't it? Because it's continuous and you're finding the area.
If you have a big so the assumption is this is your null hypothesis, okay? The assumption is that P, the probability of heads, is a half, right? That's the so-called null hypothesis. So yeah, this is a big old binomial distribution problem, right? It's humongous. So you're better off just modeling it approximating with a normal curve. If you've seen in the book, they have some binomial mass distribution things, and it looks, when n is large and p is reasonable, it starts to look like a bell-shaped curve. It's the normal approximation of the binomial.
Cool.
Okay.
So what does the 2350 represent? Is that also, it's just a one-sided,
Well, this would because
Right.
this is, you know,
that's just the other side of the
right. The null hypothesis.
reject region. Because when you subtract 5,000 from 2650, you get
Right.
2350.
Right. So the null hypothesis says it's the mean is 2,500. It's a fair coin, right? So you have to. It's not just this side. You also have to look at, you know, it could be.
Well, it's only one-sided. It's only two-sided if we're comparing two different. It's not. It's a one-sided distribution.
This one's one side, but many times it's two. It could say it depends on how the problem's worded. It could be worded that the coin is not fair, but they don't say which. They just say it's not equal to. See, if you're alternate, I don't know if you follow this, but if you're alternate, it would be like the mean is not equal to 50%. Okay, so for this, the mean of this, well, whatever, it's 2,500. It's not equal to 2,500, right? In that case, I got to do both. I got to look at both sides. It depends on how the alternate is worded.
But you're saying the probability of landing 2650 is 0, like only on
It
2650.
depends on which. Okay, if you're going to model this with this, yes. But if this is the binomial, if this is a discrete distribution, and there'll be mass at these points, right? I mean, it looks like something like this. You have it looks normal, but it's got just the tops, right? That's the binomial. That's a discrete distribution. But these things get kind of crazy when n gets large. So then you model it with a normal curve. You model it with this continuous distribution. We'll do some of this later. We'll get it's coming up in chapter 5. But in chapter 4 they show these how it looks like a normal distribution. Okay, that's some sort of limit theorem too. Okay, so
yeah, it's like the continuous is like as if you had infinitely many different possibilities. So if you were to pick just one possibility, the chance would be 1 over infinity. It would be 0.
Yeah, but right. Well, the thing is,
way of looking at it.
Certain random variables are continuous by nature. Okay, it's like if you're measuring height, people's heights, right? They could be anywhere in there, right? They're not. It's not discrete. There's certain things are a time, like the time for something to happen. That it could be any, definitely, what I mean. So it's how the experiment is defined, and whether you have to look at that, whether it's just a discrete thing or is this.
So for that to work, then you have to give it a range. Maybe it could be like
yes,
1 unit,
right,
or a tenth of a unit.
Yeah, because if you integrate unit, yes, you have to have it
to the extreme. Yeah,
absolutely right.
So
okay, so
that's just an approximation that he's using there. He's like, if we were to approximate it this way, then you would have to give it a range. But
well, it's funny. The binomial gets approximated different ways, right? It gets approximated with the normal. It gets approximated with the Poisson, and I think there's one more way to approximate it. It's like a lot of people. When you're doing these things theoretically, you've got to use these approximations. Things that are discrete don't do well with calculus.
So there's a lot of different ways to make a bell curve then.
Yeah, well, no, the problem is everything comes back to the bell curve. You cannot avoid it. It's unavoidable. And I'm getting kind of far afield what I meant to do today because this is really from the next one. But let me just give you something real quick so you can chew on this. If you had a very non-looking bell distribution, suppose you had a distribution look like this, call this a box distribution. Okay. Let's assume it's continuous. It's just a box. Okay, so all of these, equally likely. It's equally likely the random variable will be anywhere in this range. Okay, if you take a repeated samples of say 10 numbers, okay, from this range randomly, you choose 10 numbers randomly, and you take the average of that. Okay, do you understand what I'm saying now? You take a sample size say equal to 10, and you average them, Now you make a distribution of those. Does anybody know what that's going to look like?
Oh, you mean you're saying you're doing this over and over again? You take 10 samples,
Yes, right,
average them,
right,
then you
right. So
take
we're
10
actually we're making an
average them and you
approximation
plot
to the sampling distribution, right, of the mean. So
Okay.
you're picking 10 guys here, wherever they
Oh
are.
my God, it's a bell, isn't it?
And you average them, and they'll sort of cluster around the bill of this, okay?
Oh,
And you
that's
actually
crazy.
you get the bell out of this, right? It's
Whoa.
the way it happens, okay? And we can see it happening, right? You're not, in order to get something not bell shaped, you'd have to have all of your numbers randomly picked over there on one side, right? So if you don't do that, you have some over here, they cancel out, and the center becomes more likely. So this is the reason why one of the reasons why the bell curve is it just cannot be.
It just shows up all over the place.
Yes, you cannot do science. You can't do anything biology. You can't do even mathematics. It's popping up. It pops up in mathematics. You just can't do anything on the bell curve. I think I'm putting some people to sleep though, right?
I just find that fascinating. I hadn't thought of that before.
That's it. So you guys saw it. So you can actually, if you want to write a Scratch program, you could actually do it. Take these random numbers in here and take their average, plot that, and just keep on make a histogram of the results, and you get a bell.
Make the world's most inefficient bell curve generator.
Well, no, I mean, no, that's surprising. I've done it myself on a calculator.
Yeah.
The surprising thing is that it works. You'd actually, the thing that you look at, the histogram, is bell shaped. But let's get back to what I didn't do last time. And my memory is serving me correctly, which is, I hope it is. I don't believe we calculated the mean and the variance of the Poisson. We should probably do that. Oh, well, I got time. I've got time here. Okay, so X is Poisson with parameter lambda. And what is the mean? This is a very important result because, of course, it's gonna be the lambda, but why is it? Okay, why is that in the washout? So let's see. The first thing, let's go over expectation. This is the critical thing. How do you take the expectation of a random variable? So what is it? It's the sum over. You take the different values of it times the probability of taking those values. So what would that be? By definition, it's what? We have to cheat a little bit here. Forgive me for that. Okay, so it's I times the probability that x equals I. What is that probability with the Poisson? What is it? It's e to the minus lambda I factorial times lambda to the I. Okay, this is now what can be done. You probably can see that if we just put, we could start this at 1. Okay, wouldn't change anything. But if you started at 1, then okay, this is tricky. Okay, it's a little bit tricky. It's not so simple. I kind of like to just cancel out what I have here. So I know I can take the e to the minus lambda out, and I can cancel out. See, it's an I and I factorial. So I can think of it as I minus 1 factorial. And if I pull out a lambda, then I would have a lambda to the I minus 1. And I'm still starting at 0. That looks weird the way I wrote it. I'm sorry. And it's e to the minus lambda fronting all that. It fronts all that. Okay. The problem is I've got a minus 1 factorial here. That's the problem. I think that this is tricky. I think I probably should have started at what I should have. Okay, I'm sorry. Yeah, this is not a good day for me. I think I should have started this at 1 because it was the same thing. It was the same thing, but I'm just that this is legal here. I pull up the lambda, so I could have started this at 1. All right. right? Because at I equals 0, this is 0. So that term, you don't have to worry about that. We could start it at 1, it's the same thing. But then I'm just pulling out a lambda, and this, there was an I here, but it was I over I factorial, so at least I minus 1 factorial. Okay, so what to do about this? So now if I go back to 0, and this is lambda to the I factorial. And this is, what is this? Well, this is the expansion for e to the lambda, okay? Lambda to I over lambda. So this is the e to the lambda. So it's e to the minus lambda, e to the lambda times lambda. So that's lambda, that's the mean. Which is not terribly surprising because we've been using it. Lambda equals NP. Why NP? Just to review, why NP? Sorry, guys, can you see it now?
My understanding on it is the Poisson is a good way to approximate the binomial, and the expected value of the Poisson is lambda, and the expected value of the binomial is NP. So we
Yeah,
said
very good. Good. Okay, that's what I was looking for. Yes. As a teacher, if you become a teacher, you'll definitely. It happens to me in the lower divisions, or the GE math courses. Somebody guesses on the. You can kill me for saying it, but I taught Math 140, and we had huge stacks of like 3-4 feet high finals to grade, and a lot of it was multiple choice. And some people were guessing because their score was the binomial mean. I mean, we assumed it was. It was, we assumed that was happening. Okay, so what about the variance? So this, I believe I did was correct here. Let's look at the variance. So in order to get the variance, I'm going to have to calculate e of x squared. And I'm going to have to cheat. This is a little tricky. So e of x squared. I don't know if you can see that. It's a square there. Okay, so we do like we did before. So 0 less than equal I less than infinity. Now I need I squared because that's the theorem, right, or proposition that you put the function. This is the function of I here. And then what? So what is this? So e to the minus lambda, lambda the I over I factorial. Okay, so they're going to remember how this works. And there's no reason why you can't start this at 1 because this is 0 here, and I equals 0. So I started at 1. Okay, we started at 1. It's the same thing. Okay, but now so now it's time to pull some stuff out of here. So if I pull a lambda out, of there, what do I end up with? So there's still I squared. So I squared over I factorial. Let's try to get all this stuff right. So that would be, there's still an I up here, but this is I minus 1 factorial in the bottom. So e to the minus lambda to the I minus 1, because I pulled out a lambda. And this is still at 1 here. So this is a little tricky because on the next step I'm going to pull it back to starting at 0. Let's just see if I have a chat. No, I'm just quiet. So starting at 0, how is this going to change? E to the minus lambda to the I. But there's an I plus 1 here. because I'm starting at 0, so it says I plus 1, e to the minus lambda, lambda to I minus 1. Sorry, it's lambda to the I, because I'm going at 0 here. And this is I factorial. Now you can split this. So you can split it into 2 parts. So you can take the I, take the lambda, that's out of there. But this stuff you can split it in 2 sums. The first sum will be I, e to the minus lambda, lambda to the I, over it should be I factorial, but I'm just wondering what happens to the I. Okay, so you got that. And the next one is just a 1 here. So that would be e to the minus lambda, lambda the I factorial. So this other part right here, we know what that is, okay? This is the sum of all the probabilities over the whole sample space, all the outcomes. This thing is 1 because it's a probability distribution. What's this guy over here? This is just E. It's the expectation, so that's lambda. So that's what this is. So you put all that together, I get lambda squared plus lambda. I'm sorry it took so long to get here, but to get the variance, how do I get the variance now? So this is
I'm a little confused on the when you took the lambda out.
yeah, right?
Yeah.
Okay.
Why is the bottom? Why is that still I? Why did that turn into I minus 1?
This is a tricky thing, okay? This is a tricky thing. And
Okay.
why is it tricky? Let me just be intellectually honest with you. The way this is done by statisticians is something called moment generating functions. They don't do this. This is old school stuff here. They don't do it this way. But Ross wants to show you the traditional thing. So
Okay.
this is at 1, right? And it's I minus 1. See that? If you go back to starting at 0, then that means you've got to jack up.
I think I'm following that. I the denominator in the expression it goes from I to I minus 1 factorial. I'm not sure.
Oh, okay. I here starts at
Sure why
1,
that
right?
is.
So that means 0 factorial, right? So that means this thing's got to start at 0 factorial. So
Yeah, but in the second one, it's still I factorial, but it's
no, it's I minus
Like further back. Further back.
further back. Yeah,
Yeah.
that one.
Oh.
That one says
No,
I factorial.
but I didn't change. Okay, all I did is say.
So it's supposed to say I minus 1 factorial.
I just dropped. No, see. Okay, look at this. If I is 0, this thing is 0. This the term doesn't exist. So I can do this. Excuse me. I can do this without changing anything here.
Yeah, that's what I thought. But then
Okay.
why does it change in the next one?
Oh, that's easy. I took out a lambda, so that's lambda I minus 1, right? It was lambda the I, so I pull out
Okay.
that. And this was I squared. Now it's just I, right? But you see, here, you have I.
So
Okay,
like that
yeah, why is that
specifically is
just
where you
I?
canceled it?
Yeah, I canceled one of the I's. So
Oh,
I
you canceled one of the I's.
Yeah, sorry about that.
Oh, yeah, I had no idea what was going on. Okay.
Yeah, so it's tricky, right? I mean, it's tricky, but we're not quite, okay, so we're not quite done. So we've got to do the variance. What's the variance? So that would be E of x squared minus mu squared. And mu we already know is lambda squared. So we just got this. This is lambda squared plus lambda minus lambda squared. That's equal to, what is it? So we just discovered something kind of weird. The mean and the variance are exactly the same.
I haven't discovered it yet. Hang on.
Okay, well, EX squared we just did, right? We just did EX squared. We got this.
Okay. I'm trying to absorb the second line now. I see what you did with the incrementing I, And then that last step, what is that last step?
Right here.
You distributed the lambda, and
This is the definition of the mean.
okay.
We did that before. This is the mean. This is just adding up all the probabilities. If you sum up all the probabilities of the different outcomes of the random variable, it should come to 1, because the probability of the sample space, the whole sample space, is 1.
Oh, okay.
That's what this is.
Yeah, I see it now.
Like, for instance, when did we see something like this before? What other probabilities would, I mean, like, you'd have to, to be honest, the binomial comes to mind, but that's not trivial to show that that's adding up to 1, right? I mean, you want to try it? What's our time?
I'm good.
But it's not trivial. Let me check the chat, see if the chat looks good. I'm just saying that this type of statement. How do you establish this kind of statement here? Well, can I show you? This is like a scale factor. Lambda to the I over I factorial summation. That goes to e to the lambda. So e to the lambda times e to the minus lambda is 1. So that's mathematically we can see that. But what I'm trying to tell you guys is I don't think it's that trivial with the binomial, right? If you add up all the binomial probabilities, are you guaranteed to get 1? I mean, I'm not sure how easy that is. I know it's doable. I've forgotten how to do it.
So what was that thing about the variance? And what's mu again? I forgot everything.
Mu is a shorthand. Okay, when somebody writes mu, that's shorthand for the mean, the expectation.
Oh.
It's a shorthand. It's easier to do that than to make square brackets. Okay, so I mean, how would you do it for the binomial? So if you want to add all the probabilities, right? So I'm just going to add them all up. So 0 less than equal to I less than equal to n. What is it? So what is it? You choose I. What would it be? P. So this is binomial in P. So P to the what? I don't know. How hard is it to show that that's equal to 1? I don't think it's trivial. I didn't do it. I don't know how to do it. I mean, I guess we could put that on the test. Now, I know that Ross does it, but you realize that that's not completely trivial, right? I mean, because you're dealing with these weird coefficients, which you don't, know how they grow or what they look like. I'm sorry, guys. I'm not being very smart today. I don't know how this is done right now. I don't remember. I can look in the book and probably realize I'm stupid. But does anybody had read the book and they know how to do this?
Off the top of my head now.
The problem is these coefficients. That's the problem. Because there's a lot of research where there's a lot of higher math involved with those things. They're sort of, I should say, there's no like simple formula for them. You know what I mean? Like, okay, we can just take a function of something and get they're full of all sorts of properties. But I mean, what about the simple case where p is a half? Could we even do that? I mean, what's the binomial theorem? It's what if p is a half? What's the binomial theorem? We're supposed to know this stuff. I'm supposed to know it too. So what if p is a half? Then you end up with something like this, right? So a plus b, how does the binomial theorem go?
Is the sum, let's see here. So we have n choose I, if we're going to use I, times a to the I b to the n minus I. And yeah, from I goes from 0 to n.
So, okay. So, what is the case of this that we're encountering over here? I've got because it looks like what I want to do. What do we need? I need this stuff. I need the a and the b to be a half, right?
But I mean, okay. So yeah, if you want a and b to equal 1/2, okay, well then 1/2 plus 1/2 to any power is still 1.
Right. So you get with n choose I, and if they're both a half, that's.
But at this point, you could just say a equals whatever probability, and b equals 1 minus that probability, and it works all the ways.
Right. This is okay. This is the thing I don't know. Right. This is what I'd like to know what this is. That's this.
Yeah, we've just rewritten.
So are you asking about we're not allowed to use the binomial theorem?
No. I'm trying to think. This is
We're done.
It's the consequence of binomial theorem. I think you guys noticed it, right? Because you can take a and b and both a half, right? So this actually is equal to 1/2. You know this, right? You saw it. This is equal to 1. So yes, I mean in that particular case, right? But what if it wasn't that particular case? So a would be
A equals p, so where p
Yeah.
is some probability, then b
Right.
would have to equal 1 minus that probability.
and you still get p plus 1 minus
But
p.
wouldn't this mean-
Okay.
So this just means that A and B have to add up to 1 for this to be true, I
It's
think.
to work, yeah, right.
Which is true
Right,
no
but-
matter what if it's
Well, you guys,
P
but congratulations, you guys.
plus 1 minus P.
So that's it. So that's the proof. As long as we're allowed to use the binomial theorem.
You have to be allowed to use the binomial theorem. You have to. You can't, but then
Okay, now it makes sense to me.
somebody could come back and say, "Well, how do you know it's true? How do you prove the binomial theorem?" And I just don't. I don't know. You know, I mean, you could probably do something by induction or something, and I don't want to. You know, that's.
Look it up, and then we write it down.
You're talking about my other, your other class.
I just did this in 492. I can go back on my notes. I think we did it in 490.
Yeah,
We used it. I know we used it. I don't know if we proved it.
I'm trying to think. Is there any other way to? Besides induction, I don't know. But the joke about the other classes, I already told you this. I'm sorry if I repeat. Please forgive me. But they have a programming project. They had a test, right? It's all take home. I already said it, right? I'm just repeating. But they had to solve an instant insanity puzzle, and several people went to the internet, the GitHub. I already said it, right? Oh, some of you guys went to GitHub. Maybe it wasn't this class, it was the other one. They had a different instant insanity puzzle. It was harder, okay? And they were complaining. They said that the program is not functioning correctly. I don't know, it's just, of course not, I mean, never, that's the way it is with code, right? There's always stuff. So y is the mean equal to the, okay, we calculated it, right? I can't tell you, I don't know, I don't know enough to be able to tell you intuitively why they has to be the same. I don't know. I know that what do I know? Let me take a stab at something, okay? Besides the proof of the binomial theorem.
The previous example, that was with x squared, so maybe it just has to do with what you're multiplying x by.
I don't know. But I mean, if you have e to the x, right? So you want to know the derivative at 1. It's e, right? So it's so, this is a sort of similar thing. I mean, I know that I know this is a real stretch right here, but e is the only function whose derivative is its value at the points, right? And I'm thinking that probably is some relationship to the Poisson distribution because you're dealing with an e, right? E to the minus lambda. I mean, it's an exponential kind of situation, and maybe the mean and variance somehow. Of course, this is a stretch, right? I'm sorry, this is not my specialty, but it may have something to do with this uniqueness of the exponential function. Okay, I'm supposed to,
Makes
let me
sense.
check my time. I've got 4 minutes. I'm supposed to show you the hypergeometric. Can I just show you something else? Just real quick, okay? Just something different. Just, okay, it's from the next chapter, so I kind of want to get you excited about the next chapter, and nothing better than just this really quick kind of paradoxical thing. Okay, if you have a circle, let me see if I can draw a circle, and you want to take a random chord on there, a random, a chord at random. You know what a chord is, right? Like F major, or no, a chord. You know what a chord is? Yes or no?
That's something that like bisects it somehow, or like intersects 2 points.
That's a
Two
chord.
endpoints on the circle.
Yeah, right. That's a chord, right? Have you seen this before, Aim? This is some sort of.
I have no idea where you're going with this. I'm curious.
I showed it to my dad, and he was flummoxed by it. So I guess some people know this.
I mean, I don't think I've seen this before. I mean, aside from I've seen a chord before.
Oh, okay. So the problem is, say, what is the probability that a random chord is. Take a chord done at random has a length longer than this inscribed triangle here. So what length are we talking about? We're talking about this length, or this is equilateral, it's just inscribed. So what's the chance that a randomly drawn chord is longer than the length of a side of an inscribed triangle? You don't remember what an inscribed triangle is?
There's
You're
like
supposed to have
history,
an
right?
eye here, right? Like a dollar bill or something, whatever. But
I'm not sure if I understand the question.
Okay, this is a distance. This length is set.
Oh, are you saying like you taking like are we picking like 3 random chords or
No. I'm just saying, how do you define this L? L is the length of the side of an inscribed triangle. Okay.
Okay.
And the question.
Oh, the length of one side. I thought you meant the whole circumference.
No. What's the chance
I mean, the whole
a chord at random that it's going to be bigger than L? So
okay.
let's draw a chord at random. How about this one? Is that
Wait, the inscribed triangle, is that an equilateral triangle necessarily?
Yeah. It's 60-60-60, right?
Okay.
Do you guys? This is actually slightly profound kind of thing.
I would bet it's 50-50.
I guess it's 1/3.
Oh, you know it then. You know.
No, I just did the problem, and I mean, I don't know if I did it right, but
How?
I
can show you my logic for
Why did you
it.
do that fast?
Okay. Yeah. No. Aim, you should go immediately to UCLA. I'm sorry. I don't care if I get reprimanded for saying it. You really should. You should do something. Because you know what?
I'm trying. I'm planning on going into math. So.
Yeah, but this is way different situation here. But here's the answer. What would be the strangest answer to both of you guys at the same time? So Aim got 1/3.
1/3.
Ethan got 1/2. What would be the most amazing thing to say about which is correct and which isn't?
That they're both correct.
Very good. Who said that? Christopher? Or who said that?
Yeah, that was me. Christopher.
They're both correct. How the hell can it be one thing and also another? It's a probability.
What? What?
And actually, I have to admit, you guys, I don't remember if it was 2/3 rather than 1/3. But still, the fact she got 1/3 to me is you're in there. You're in.
Okay. Well, first and foremost, I just set up what I think might help me answer the question. The way I did it is you put 1 point down.
Okay. Let me do that really quick here. So you put 1 point down. Yes.
Right. So you're given a point.
Yes.
And from that point, I drew an equilateral triangle. So that's one of the points on the triangle.
Oh, the equilateral triangle. So.
Mm-hmm. Yep, exactly, like that. Mm-hmm.
Yeah,
that's what I did.
Know how there's 2 different answers.
Right. Cool. So the sides on the left would be shorter, but across anywhere along that circle would be
very
longer.
smart.
So that's 1/3 of a circle.
What you're saying is you're dividing this from this line right here. You're dividing into 3 things, right?
Right. Yeah.
They're all apparently the same. So which which
If
percent?
it goes to the left, it's too short. If it goes to the right, it's too short.
So
But if
you're
it goes
dividing by
anywhere
which-
in between,
Maybe
they're
it is
going to
1/3.
get longer.
I have to check the book. Maybe it is that's a reasonable assumption, right? Because
Right.
Angle is
But,
random.
I mean, I'm not saying that if there's something I'm not considering, then sure. But
I see.
that's what I thought is.
So you're definitely weighting with respect to the angle. So it's like
I'm
assuming
not
it could
really
go
thinking
any
about the
direction.
angle. I'm thinking about just points on the circle. So kind of.
Yeah, but it's
because a
divided
chord
by
is
the angle,
2
really.
points on a circle.
So
Well, okay. How did okay? I think you have it. Okay, I think I didn't remember it correctly, the statement of the problem, but I think that's correct. 1/3 makes sense to me. Now, Ethan, how did you get a half?
I totally guessed.
Oh,
I thought of like the
Don't
average
overrule.
length. Well, here's what my brain probably did in the background as I was guessing. You see a circle and you just slice it up into a whole bunch of different little strips, and I just figured what's the average length of those strips, and I thought it would probably be around around L. So I was like, yeah, it's gonna be 50-50.
This is right. Both of you guys are both right. I don't know. You don't read the book, do you? I mean, if you read it, you probably.
I kind of just thought of that just now. I was guessing. I couldn't explain
Let
it
me see if
before,
I can
but
get anything right. You're saying
now
that
I think
here's
that's
the center.
what it is.
Here's the center. I think what you're saying is that you could have placed that chord anywhere along this thing. It doesn't matter where it is. It's anywhere along here. So half the time it's going to be here. Half the time it'll be here. So when you're down here, you're too small. So you're bigger, right? That's 50-50. Is that right, Abe?
Right. Well, the chords
it,
are
Abe?
in. If it's anywhere along there, then they're all facing horizontally. That's.
Well, but it doesn't matter. It could have been anywhere, right? I mean, but you're right. But these are, they're all horizontal. I mean,
I guess.
you shifted this anyway.
I guess it could be anywhere. Yeah.
Yeah. So I think you got.
Yeah, you're right. Okay, so that
Then
that
you go
makes
back to
it make
Aim.
sense
You
from
see
any direction.
his approach, Aim? I mean, it's different, right? But it's
I need a second. So the idea being, so you have a radius there. If the chord is lower than that point, then it's shorter. If it's higher than, it's what's
Longer.
it called?
right.
Yeah, it's longer.
Right.
I guess I mean, I would need a second to think about it, but that doesn't include every single possible chord.
But actually, it does. I just realized that our teacher, he just explained it. You're saying that they can go any direction, right? And
Right. The other point could have been anywhere along, from the center.
yeah, and no matter what, if they pass through, if it's a chord, then it passes through that radius. Then that holds true with whether it's within this segment, it's going to be larger, and within this segment, it's going to, irrespective of what angle.
Well, this is the most amazing thing that's occurred to me in a classroom in all these
Holy
years.
cow.
But
So I guess this is like that other.
paradox, and it has a name to it. I think it's Bertrand's paradox or something.
Well, this is like that paradox that boggled my mind that you told us about like way early on. That was like had to do with like there's a my first the youngest is whatever, and I thought that had no effect on it, but it did have an effect.
Oh, yeah, but that's
maybe.
just a question of verbiage. Oh, wait,
Well, yeah, but maybe it's the same thing here because AIM solution assumes that we at first pick a point and then go anywhere we want. So maybe not all points are like equally likely, or maybe there's a condition.
You're actually closing even though I'm over, you're actually finishing my lecture. But
Oh, sorry.
I'm worried. I don't want to get I don't want to close it if AIM is still not. I'm worried about pushing this too fast. Maybe this is some geometry, right? To
For
know-
what it's worth, I was curious and I Googled it, and MIT has a very, very cute little, not just description, but a way to set it up so that it doesn't give away the answer right away. But there are multiple solutions, and there's one more, and I'm not going to click it. The other answer is 1/4.
Oh.
And
There's another?
yeah, there's another one. There's 1/2, 1/3, and 1/4. I'm tempted to click it, but I want to see if I can figure out how could it also be 1/4 somehow.
1/4 is probably where you're picking two random points, one here, one there.
Okay.
And you pick them both independently and randomly.
Hmm. Well, don't give any hints because I want to think.
Yeah,
about that too.
I want to think about it too
To me, the
before I
hard
click
thing
on it.
to me, that's just maybe because my geometry is non-existent, but I had trouble with the half and half here. I wasn't sure that split this. If you have an equilateral triangle, I wasn't sure that this leg split that radius. In
Yeah.
half. It does, but you have to
Again, that's where my guessing came into play. I was like, oh, it looks like it's about a half.
you have to do some potentially some trig but my geometry is. But okay, you guys. I mean, this is a pretty big deal because this is a famous. I think is it Bertrand's paradox or some other.
Yeah, that's how I looked it up. I looked up Bertrand's paradox chord, and there's a little MIT web app thing. It looks pretty fun, and I'm checking it out now.
The
This
one
is
quarter
like-
solution is not even like what you said had made sense about picking 2 points on the circle and then drawing the chord between them, but that's not the 1/4 proof. And now this problem is even more confusing because it's picking a point some distance from the center of the circle and then walking a straight line to an edge.
Well, you can think of it that way. You can also think of all these chords, which ones, because it could be anywhere, I mean, you take a chord, it's some distance from the center, right? So you're saying, how far away is your chord from the center, right? That's what you're really looking at. It could be 0 up to the radius of the circle, say 1,
I guess the lesson learned here is how many different ways there are to draw a line.
You have to be careful. No, the lesson is deeper because the lesson is saying you have to be careful when you run an experiment, right? Because the experiment was to pick a random chord. Apparently, the answer depends on your machine or your procedure for selecting a random chord. And this you would never have expected it because it's anti-intuitive. It's not like random's random. We know, like flipping a coin 50-50, we get it. But when it becomes to geometry, if you're going to do something randomly, you've got to be careful. You need to be
That's
careful.
so cool.
But this is chapter 5. This is stuff that happens in the continuous random variables. Okay, this is not a discrete problem at all.
That's really cool.
Well, thank you, Matt. I've never seen, and I present this sometimes to 400 level class, and just don't really.
I did not expect to be right. Like at first, I was just 100% guessing. I only thought of like a vague explanation afterwards.
But okay, guys, I think we better not make force with other people that hang in there. I guess we're over. But for Thursday, I will try to really finish chapter 4 done with. We have to do the hypergeometric distribution. Then we'll go to chapter 5, the continuous things, and then continue the march towards the end of whatever we're going to do in the class. This is really this is called geometric probability, and that's not the stuff that you use for statistics. This is something else. Statistics is, a lot of people have a dim view of statistics. It's like hard work, and it's not pleasant. All right, you guys.
So it looks like the bottom line of how you get the different ones is how do you select the chord?
Yes.
Yeah,
That's really what it is. So it depends on how you pick it. That's what I'm seeing here with this little demonstration.
Right, but isn't your intuition that random is random, right? I mean, if you picked it random,
Right. Yeah.
it should be good to go.
Random is random. You're right. It does kind of, like, you wouldn't think it would depend, but it does.
So that means we can't trust our intuition. The way we set up an experiment, we can't trust ourselves to believe. there's different ways to be random, I guess.
Yeah.
What's that
Right.
synonym to random? There's a word, I forgot. I used it forever.
I'll see you later.
All right, Ethan.
Yeah, have another class. Take care.
All right, thanks for all that. Okay, guys, everybody else that hung in there, thank you so much. See you on Thursday. If I'm still alive.